good evening. It's my privilege to be talking to you online on the promise and potential we see for AI and how it affects us all, whether we are in the business of computing or simply benefiting from computing. AI is now claiming that its machines are not just number crunchers, but they can actually make decisions as well. And if you think about it, this has far reaching implications. There are large areas of society that do need improvement. They need fundamental efficiency improvements. These areas of societies are dominated by services led by humans, better than average human. Because remember, most of us rely on for our services, not necessarily best human. We don't have access to best teachers or the best doctors. We have generally access to, if we're lucky, if we have access to better than average teachers and doctors. Machines, therefore, if they can do as good a job as an average teacher, average farmer, average doctor, they can actually offer services and they can help us in those areas of societies that do need significant efficiency improvement. This is the power and this is the promise of AI that has us all excited because it affects a large area of society where computing today has very little to do. And this, if you think technically, this has become, we have in a way known this, seen this coming. It's just that it was so far, we're not quite there. Why? Because we could solve a class of problems where we primarily had to do with lots of compute, meaning inside out problem where we were given nice equations to solve. But anytime we were outside in driven where we did not have good analytical formulations, we were pretty much, we didn't know what to do because we knew in principle we could actually reverse engineer a model based on data by simply observing input output data and coming to trying to reverse engineer a model from outside in. But we just never had enough data to be able to reverse engineer good enough model. And the test for such goodness of a model is very simple, that if I do the forward pass again, is the model good inferencing or actually predicting good enough? If it is, then it must be good enough model. So this outside in perspective, outside in ability, which is what pretty much 99% of the problems are looking for, that capability is what we had lacking. And now we finally have enough data and enough understanding, algorithmic understanding, and enough compute to be able to do both out, not just inside out, but outside in as well. Now, this is the reason why you see that the AI compute needs are skyrocketing through the roof, right? Even if we had an multi-exaflop machine, like 100 exaflop machine, take multi-hours to train for a game like AlphaGo. It's still a game, okay? But it does take that long to train a machine. And this is what is called, what has all compute companies and compute technologists like many of you excited. The promise of this has us all excited. Now, this is still, like I keep referring to, still the beginning, because reality today is that machines are only getting better at sensing tasks. They'll soon be better at reasoning tasks. And it's not just enough to get better at these tasks. We need to get better at scale, right? By scale, I mean at population scale. That's one good way to look at it, at the scale of population. The promise of AI is that we can learn from all to serve the one, meaning a car can actually learn from not just its own mistakes, but from the mistakes of every car driver, every self-driven car around the globe, and get better without it itself making those many mistakes. That's the promise of AI, right? Now, learning at population scale is non-trivial task. Currently, not much. All we can do at a large scale population is probably stream a movie or maybe support shopping, and even that becomes hard when the whole world tries to go shopping one day, same time. So supporting such real-time decision-making at population scale is non-trivial. And that's what we need to do for either to deal with pandemics like the one we are going through now, or in general to deal with real-time decision-making at the scale of population scale is non-trivial. And I'm showing here an example of the kind of stuff we could do and we need to do to be able to support needs of simply the health needs, right? Where we can actually understand and explore multi-omics, right? Not just genomics, proteomics, and microbiomes. And we understand better, both inside out and outside in, how humans react to a certain environmental condition or some virus mutation, and what do we need to do real time. And that need needs to be personalized. Okay, just like a car has to make its own decisions, humans also have their own personalized needs. And can we meet such personalized need real time? And that is the promise of AI, and something where we are only seeing the tip of the iceberg, and we have a long way to go. Now, what it really means in computational terms, in data center computational terms, is what I've tried to capture here. Currently, most of AI compute is summed up in small matrix dense algebra, which is what you see at the extreme right side of this picture, right? Where if you have dimensionality down to, let's say, few thousand, like ImageNet 1K, 1K, if a complexity of it will be 1K times 1K, it's some of the order of millions n square. Not bad. That's what we can handle today, okay? But most problems are very, very high dimensional. They're not just 1K, but they're millions. And for such high problems, we have to be able to deal with sparse nets and not just dense nets. The sparse processing is where we are beginning to now make inroads. And how do we really, and that's critical, that's at the heart of our ability to be able to shrink the time down to the complexity down. We have to start with very high dimensional and reduce hierarchically that dimensionality. And this is at the heart of our processing need for coming decade, where the focus will shift from dense processing to sparse processing. And all of this dense or sparse processing ultimately needs to be fed real time with data sources. That's the data management part. Before any arithmetic or floating point operations begin, there's a huge need for data management. So data management and sparse net processing will become the dominant data center innovation sources, and not just the dense flops that we have been so far mostly focused on. So with this in mind, we have been working on these next generation problems, namely graph analytics, where efficiency today is very low, unlike 90+% for dense processing. Sparse processing for large graphs, and especially large dynamic graphs, machine efficiency is pretty low. And this is what we are trying to address and improve, working with thought leaders around industry. If we can do all this, we can actually go a long way in trying to meet the demand cycle of AI. But while this research goes on, and while we have been doing this, something else dawned on us. And now, shifting gear, I want to focus a little bit on what exactly is a new problem that we are increasing. That it's not really a new problem, but the realization of it is, at least and for many of us, is new. And that problem has to do with the growing cost of programmer productivity, meaning writing not just a functionally correct, but a performance software. Remember, all of AI is not just about writing correct code, but highly performant code. The need for performance is skyrocketing. How do you write a correct and performant software is increasingly becoming expensive and painful, even without any AI. Just the burden of software and the poor software quality, the software quality costs have been skyrocketing. I've cited here a study that actually talks about the cost of poor software quality in trillions of dollars, and that was a few years back. And most of it, almost 50% of the cost, is in writing, and not just writing correct, but debugging the poor quality software, right? And this is increasingly getting harder and not getting easier. And this has this is a significant problem because we're not just talking simple software, we are now talking complex software, a software that needs to do a real deep math, not just the sort of stuff we have been dealing with so far, but deeper, harder stuff, right? Where we have not just performance need, but real-time performance needs. And so we have shortage of software developers in general. And here we are talking ninja software developers who are barely 10% of programmers. Therefore, there's an acute shortage and growing shortage of people who can program such machines. Okay, so it's not just a matter of designing such machines, but making them performance productive, making them easier to program, easier to code, easier to for the code to be debugged and understood and maintained. So this is a significant industry challenge, and this challenge, interestingly, is only growing in the context of AI. Earlier, we would be writing C code, let's say C++ code. Now, we are talking about not computer scientists, but now we are talking about data scientists, right? Data scientists are writing MATLAB-like code. So Python is the most growing language. And as you can see in this paper, the gap in a poorly written Python code versus well-optimized code is not just 10, 100, 100x or 10x, but 60,000-fold gap. That's how big a gap is there. That's how much performance you're leaving on the table if you do not have a fully optimized, a well-optimized code. So here's the problem, that you're now talking about a large class of developers. In fact, the most growing class of developers are Python developers, data scientists, right? And we're not no more just talking million, we're talking now hundreds of millions of such growing people who want to access power of computing, who want to have performance of computing, right? At the level even beyond most high performance computing scientists of yesterday. So their performance needs are well beyond exaflop. On the other hand, their willingness to learn a new language, a new MPI or a new CUDA is pretty much non-existent. So that doesn't compute. I mean, you need even more performance, and your willingness to learn and a bit of computer science or computer system is pretty much non-existent. So that's the problem we're dealing with, that we have a increasing need for performance. On the other end, we must find a more productive way of delivering that performance and not simply teaching yet another new language or yet another complex piece of programming. So this means that it's at least we internally concluded that it's time to switch gear, and we should not just be talking about designing hardware software to meet AI needs, which is what first part of my talk was. But let's switch gear to now actually seek AI's help. I mean, who do you call for help these days for any problem? AI. So we're calling AI to help its own challenge. And let's seek AI's help in actually being able to deliver the software hardware needs. So this now we are therefore trying to match the virtuous demand cycle I earlier talked about of AI with a virtuous supply cycle of AI compute, that rather than only designing software hardware for AI, can we also now use AI for software hardware design itself? And if we can design it, the machines or the needs of AI sooner, better, the hardware and software, we'll be able to do more AI and design better for AI. So not just designing for AI, but designing with AI. And this has been our added focus over last couple of years or so. And this is pretty much, this had us look at the at more fundamentally where we are today. And just like I earlier talked about this division of labor, we are talking now about a similar division of labor, a new division of labor between human and machines when it comes to programming it. Currently, humans are pretty much involved in expressing their intentions of what the problem they're trying to solve, and then coming up with the right, most performant algorithm and data structures, and then encoding them and maintaining that code. And as we all know, that this is not an easy task. I mean, even though humans are supposed to be better at being able to explain things than machines, at least that's the perception. That's not necessarily true when it comes to coding. a programmer generally doesn't understand someone else's piece of code. They often land up writing their own. The human code is not necessarily most readable or explainable, but they're the best we have. So humans do not just intention expression, but algorithm development and system implementation, all three. What we're talking about now is that let's revisit this, and can actually machines do some part of it? And this division of labor, this separation of concern, quote unquote, is what we're talking now, where humans will primarily or mostly focus on expressing their intent, okay, through a high level programming of some sort, let's say MATLAB like, okay, or ideally even more natural language like. And machines, on the other hand, would actually do both algorithm and data structure discoveries, and not just one time, but adapting it and keeping it up to date over time as hardware changes or new concerns or new learnings emerge. With this vision, we have been working with thought leaders of the industry, of AI industry, such as the names you see here, and we wrote this paper, which I have reference for here. Feel free to take a look at it, on the 3 pillars of machine programming: intention, invention, adaptation, and with leaders primarily of MIT, including Professor Josh Tannenbaum. Now, the question again, why now? And the reason why now, why we can do this now, is primarily because, not just because we understand these formal methods better and we have better hardware, but also because this is a time when we have a huge amount of data, programming data for machines to learn. Remember, GitHub repository used to be only 33,000, few thousand, tens of thousands in 2008. And now, 10 years later, in 2019, it's more than 200 million, probably closer to 500 million now, GitHub repos in this year of 2020. This is a phenomenal growth, and this tells you that we have huge amount of data, code that machines can actually train themselves on to become better coder. Now, with this vision in mind, we have been actually trying to test it out, and early results are very encouraging. I give you an example, just 2 different examples here. The first one comes from our, again, work in collaboration with MIT on learning how to do database query optimizations. Remember, you're talking, primarily what database queries do is try to figure out, try to manage the cardinality of data, the amount of data that you have to touch in response to a query. And if you can do the right thing and only minimally touch the data that you must touch, and the query response time is significantly improved. And that is what you're looking for, that plan of how do we really figure out a good query plan that minimizes the response time by managing the cardinality of the data. Now, what we have done here in this project is learn this end-to-end query plan through some training examples, and our goal was to see if we can actually, how good can we do, and to our surprise, we were actually able to not just meet but even beat fully database query optimizations, not just for Postgres SQL, but even for commercial optimizers. Now, these commercial optimizers have tens of years of human ninja goodness in them. And a learned optimizer was the fact that it was able to beat their performance. Not just, remember, it didn't just beat it, but also took care of tail latency, which is a big thing, right? So we improved tail latency, and we were able to beat not just open source, but commercial optimizers in databases, and learned very quickly. This Bao paper, as I have a reference for it here, I encourage you to take a look. And this gives us, it's a fairly a promising result that machines can actually beat ninja query optimizers, which have been learned over many years, decades, in fact, and in just through few hours of training examples. And then continuing further, I'll share one more exciting result, and this has to do with machines learning how to find similar code samples. Okay, so they're trying to infer. A machine is here given code examples, and it needs to find similar code example. Okay, now there have been several research papers in this area. The one I'm referencing here is our work. Working with, again, Georgia Tech and MIT academic thought leaders. And all we have done in terms of detail, with respect to prior work, our improvement here is that we are now capturing the semantics of through a semantics tree, and we have this ability to capture semantics, and now therefore we can better learn similar code sequences. And just before we go there, just think, if machines have an ability to find code sequences which are similar, the use cases of such a capability are enormous. It'll be quite transformational if machines can find similar code samples. You write a code, simple code, and machines can find equivalent codes without you looking for it. And if one of those code happens to be highly performant code, you didn't write that high performant code. That highly performant code was simply picked by machine based on you writing a very simple code. Often that idea is called verified lifting. So such powerful use cases exist for a capability like this, if we could develop such a capability. An exciting thing is that we in fact do believe that this is doable now, and we have trained it, tested it on more than 300,000 full C++ programs in these two repositories that are listed here. In all cases, our results for MISM are better than prior such results, recently published ones. So this gives you and the reason to believe that we are almost there, where machines are actually now able to find code samples once they are trained, right? Data-driven learning. And this has, as I just said, that significant implications. Let's just pause and think. When AI enabled some few years back image search capabilities, where machines were finally able to beat best humans when it came to just simply picking images, right? Like cats and dogs in ImageNet searches. Thought leaders were able to put forward a vision for machines replacing human drivers and self-driving cars, self-driven. So now, as AI is getting closer to superhuman code similarity search, where machines are not finding similar images, but they're actually able to find also similar code samples, we can also now begin to imagine machines replacing human coders, right? So we have this bold vision now of machines, quote unquote, ultimate harakiri, where we are ready to be replaced if and when machines can. But whether we ever get there or not, the productivity boost that we'll get as machines get better and better at coding tasks is enormous. And like I said, this is what the big challenge that we have been facing of programmer productivity, where more and more people have a need for performance, but they do not have interest or willingness. They are domain experts, but not necessarily in computer science or computer systems. And how do we expand the reach of computing to them so that they can also actually benefit and from huge amount of compute power that now resides from edge to data centers? And I think we are almost there, where we can match the demand cycle of AI, virtuous demand cycle of AI compute, with virtuous supply cycle of AI compute. So with this, with this vision, we have been working with our industry collaborators, such as Google and Microsoft, and we co-funded this research at MIT CCEL, the pun on that name, DCEL. We created a new research lab there called Data Systems AI Lab, with pioneers in industry, Professor Turing Award winner, Professor Stonebaker, Professor Sam Madden, Professor Tim Kraska. And this lab is focused on this vision that I just went through, on how can machines learn data structures. Machines do better data management, how do we build data systems for AI and AI for data systems. That's the goal for this lab, which was launched in last year, and now in its second year. And the research results I showed earlier are actually output of this lab. So now to sum it up, I think we are at an unprecedented convergence of massive data with massive compute. And this confluence is going to have a long lasting impact, not just on how we do computing, but what computing can do for us. A large class of problems that so far have not benefited from the power of computing, from power of Moore's law, will now be able to benefit from Moore's law, from computing. And these are areas of society, like I said, which actually do need significant efficiency improvement. We do need more efficiency improvement such that we can feed more people by improving crop yield, such that we can develop vaccines sooner, in year as opposed to 10 years or 100 years, such that we can respond to a bridge collapsing before it does collapse. And that's where we see the promise of AI and AI's potential in terms of making machines better and more capable. Thank you so much. It was an honor and privilege to be talking to you guys, all of you. Thank you.